Hello again, and let's delve into the next topic of our Future of Light module, IMSE drives LED advancements. As you heard in the previous presentation, IMSE is a great technology for creating both functional and non-functional illumination effects for example, human-machine interfaces or parts that provide decorative lighting in cars. And to produce light, we of course need LEDs. In IMSE, it is not possible to use just any component available, but we have to select components that come in packages that survive the IMSE manufacturing process and especially injection molding, without compromises in the component interfaces or performance as a whole. Therefore, we work together in close collaboration with our partners Osram and Melexis in finding and developing IMSE suitable LEDs and controlling mechanisms for them. And today we will hear a joint presentation from Stefan Pavlik from Osram and Roland Steger from Melexis. And then later on, Michael Prandl from Osram will join the Q&A session. Thank you, gentlemen, for joining us today and welcome. But first, TactoTek's principal IMSE integration specialist, Tomi Simula, will tell us more about the LED selection for IMSE.
Thank you, Tua. Now, as we heard in the previous segment, light often forms a very core part of IMSE. We learned a bit about how light can be guided and shaped from our famous light bender Pasi and also Matthias from Lightworks. And we got a recap on how IMSE is done in general. This means that now it's safe to move a bit deeper, how light is produced and how that production of light can be controlled. As is almost always the case these days, light in IMSE is produced with LEDs. They are pretty much everywhere. LEDs or light-emitting diodes, they are semiconductor components that radiate a relatively narrow band of wavelengths or photon energies, which is a very fancy way of saying that the light that they emit is always colored, and the color usually tends to be very pure. Now, in order to get white, you would typically use a blue LED and use a phosphor to down-convert some of the blue light into other wavelengths to get a full spectrum of colors. That's a world entirely of its own, and we won't be going there today, so let's focus on the colors. There's one detail about the deeper technology points that I'd like to highlight, however. IMSE uses LEDs and other components and also materials in a very unorthodox fashion. In practice, this means that not all standard components will work as they are, and we will also need to make sure that those that do work will work for a very long time. This is why we at TactoTek have a continuously running certification and evaluation program that scouts the market, selects the most promising components and materials, tries them out in an IMSE structure using IMSE-specific footprints for components and processes. Then we torture them a bit, and then we check whether the materials or components have survived the ordeal, and if they have, then we can certify them as suitable for IMSE. There's a whole separate webinar for this, which can be found on the internet as well. The database of certified materials and components is then made available for our licensing customers, and they can then start using those. We, of course, also use these materials ourselves. Now, because this material takes quite a bit of time, and also because time is money, also money, we try to make sure that the components or materials that we certify, that they have plenty of use cases. It makes very little sense to go through all this trouble and not use the information for anything. Of course, the most time-efficient way to ensure that the materials and components are also friendly towards IMSE, in addition to being or to provide benefits towards traditional electronics, that's to educate, cooperate, and co-develop, which is why part of the reason why we are here today. Now, we're fast heading towards the darkest days of winter in the northern hemisphere, and everything is painted in dull browns and grays, and everything's really gloomy and depressing. So let's return back to the bright and beautiful colors that we so missed from last summer. Now, depending on what exactly the LED chips that produce the light are made of, the intensity and the exact color of the light that they emit may shift ever so slightly with temperature and power level. This may not be that big of an issue in an application that is always used indoors or has a very short expected lifetime. But if we have an application where the quality requirements are far stricter or the expected lifetime is very long, then things change. As an example, an average person in a developed country spends quite a bit of time in his or her car. So he or she will have plenty of time to note that the lights on the driver's door are just slightly bluer and brighter than the LEDs on the lights on the passenger side door. And additionally, since not very many of us are able to buy a new car every 2 years, the solutions that are provided to vehicle use, they need to have a very long service life. This is, of course, also a good thing for the planet, because if we bought new cars every few years, the planet would be even less able to carry on with our nonsense. This means that the level of quality that's required from the lighting solution also largely dictates the complexity needed from the LED driving solution and the selection also of the LEDs themselves. We see this a lot, that branding with light and color, that's an ever strengthening trend that we see not only in the automotive, but also on the consumer market. And this has a very direct effect on the quality requirements that our customers place on the light. Brands can be very picky about this, since it forms an anchor by which customers can identify them. It's a part of their identity. It would, of course, be very attractive to be able to get away with a very simple solution where you just slap a current limiting resistor between an LED and the power supply, but the result that you get this way is hardly ever good enough for any more strict requirements than simply having something. So a smarter driving solution is typically needed. LED driving, especially for more demanding market segments, can be a fairly complicated matter. And since the lights usually need to be controlled in more sophisticated ways than simply being turned on and off, a communication method between the host system and the LED driving solution is also needed. And usually it would be of extreme benefit for the LED driver, or at least the software behind it, or the software on the host side controlling the driver, to know something about what it is that it is driving. And that also needs to be arranged somehow. This can be compared to going to a restaurant and ordering today's special. So you will get something, but you can't really be sure whether you're going to love it. Now, producing light, controlling this production of light and arranging a good path for the light, they, especially in the context of IMSE, they tend to be complicated and multidisciplinary matters. You need quite a few people to make things work. This is why we need friends like Lightworks, we had just heard from earlier. There's just under 100 of us at TactoTek, and so many details to keep in mind. I say friends and not just partners, for a very good reason in this context. We need the deep, open relationships to make sure that everything works as it's supposed to, and that we all understand how IMSE technology ages, how it can be built in an affordable fashion while keeping the attractive value proposition, and how it withstands environmental stress and stress of everyday usage. On the topic of the light path and substrates, or the injection molded polymer that forms the bulk of an IMSE part, and the smart film substrates that form the external surfaces, you'll be hearing from Covestro in just under an hour. But now our focus here is the controlled production of beautiful colored light. For that, I'm absolutely delighted that our friends have really given this a great deal of thought, and they now have a solution on how to produce this light with the right colors and also keep those colors for quite some time. So Roland and Stefan, it's time for you now to show off the new stuff you've developed. Thank you.
Yeah, hello. Also a very warm welcome from my side. I'm Roland Steger I'm here in behalf of Melexis today, and I would like to start my presentation with the difference between automotive and consumer lighting. Customer stripes are available from hundreds of suppliers, but there is a huge difference from LED to LED. The automotive world is completely different. In automotive, we have a harsh environment, a wide temperature range, and we need a very accuracy in color mixing and brightness control, and also a fast and robust communication. We need diagnosis feature and to a certain extent also an ASIL level. Next page. What are the requirements for LEDs in automotive? We need a wiring across the car. This has to be IMSE and ESD robust. It has to be easy to implement, easy to use, and it has fulfilled the tight OEM requirements. We have to meet also the cost targets of the OEMs, and the development is done according ISO. We have to ensure a high quality level and also a long-term availability.
Hello, I also want to welcome you. My name is Stefan Pavlik. I'm at the marketing at Automotive Semiconductors. Coming now to the LEDs. You may think driving RGBs is the same like driving single color LEDs, just with 3 colors. But there are some items you have to consider. As for RGBs, 2 different material systems are used. For red InGulp and InGun for blue and green. For this reason, temperature behavior is different. For example, the red degradation is higher than for blue and green. In addition, there's a dependency for green between wavelength and current. That is why we propose to use PWM to prevent this issue. Besides, you have to choose the binning size carefully, as it determines the area you can cover in the color triangle. Not only the RGB LEDs influence the color accuracy, also the human eye perception is a factor to keep in mind. Once you have considered all these effects, you have to make sure that the resolution of your system is high enough to drive the LED in the way necessary to meet the wanted color target. After talking about the behavior of LEDs, which are products for the IMSE concept? First, I want to introduce you our brand OSIRE, which covers all RGB LED with automotive qualifications. In the OSIRE portfolio, we have RGB side looker, the OSIRE E5515, which has a similar performance as the well-known RGB 6-lit multi-LEDs. All chips are individually addressable, and the light out coupling height is just 1 millimeter, which is ideal for in-coupling into light guides. Even though RGB is getting more and more popular in the automotive, there's still a high demand for single colors. For these applications, the Toplet 1608 is the package of choice, combining the performance and the quality of the well-known Toplet just in a smaller package. And besides, the package size 1608 is also very familiar in the industry. So Toplet 1608 is offering the whole automotive interior color range. As just described, there are several points to consider when driving RGBs. So we thought, how can we make the life of our customers easier? For this reason, we developed the OSIRE E3323. So what is the advantage of this product? It provides the measurement data of the LEDs, so no necessity for customers in developing and implementing a measurement process. The data are provided via a DMC code, which is a kind of running number. The measurement data is provided are the X, Y coordinates, the brightness, and also the forward voltage. Moreover, these data are not only available at one measurement point, they're available at 10 and 50 milliamps, increasing the accuracy of the applications requiring a wide brightness range. The package itself has a low height of only 0.7 millimeters and a common anode approach to achieve a narrow out-coupling area. From performance, it can be driven at 50 milliamps up to 110 degrees Celsius.
So what we do to ensure the communication between the LED drivers. From the lens side, we used the simple protocol the self-synchronizing feature, and also the easy-to-use capability. From the CAN side, we use the high-speed feature, the automotive-proven Y, and also the robustness of ESD and EMC. And out came our Melibu, Melexis Light Bus. And to say that here, this is not a concept, it's in volume production today. Here the solution with our multi-channel LED driver. On the left-hand side, you see the master. It contains only standard components, an MCU, an UART, the CAN PHY, and to the car interface, you have the LIN, CAN, or Ethernet. And if needed, you can also include there a DC-DC converter to reduce the power dissipation of our LED drivers. On the right-hand side, you see an LED module with a flexible design where you can also flash over the air if needed. We have also integrated the CAN FD physical layer and also voltage regulator. We can measure the LED temperature without any external components. So we have a very robust module-to-module connection. So you can run the wires even through the car if needed from one module to the other. Next slide, please. Here, a little bit more about the inside of our 4-channel RGB driver. You can supply the driver with the automotive voltage between 5.5 and 18 volts. You find in there 12 calibrated current sources, 12 PWM stages to control color and intensity. We measure the temperature of each LED indirect. We have a multiplexing capability integrated. We have diagnosis features. We can detect open, short, and also threshold voltage. You can update the LED drivers via the bus with hundreds of LEDs without any delay. And our device is already ready for the DMC code from Osram. This DMC code is stored directly in the LED. And the development is done according ISO to a certain AC level. Next slide.
So far, the products have been described. But how does this approach look like in a manufacturing process? When all components like LEDs and controllers are ready for production, the first step is the pick and place process. In the usual process, the next step is measuring the LEDs. But if you use OSIRE E3323, you just have to scan the DMC code to get the measurement data. The final step is calibrating the system. This is the usual step, but here you are flexible in using your own software, or you make use of libraries which are provided by Melexis. To verify the interaction between Melexis controller and the Osram LED, a demonstrator had been built up. One key element for the whole setup is the barcode reading. Therefore, we check two systems, the Microhawk ID40 and the Keyence SR2000. Both systems could read the DMC code without any problem. Besides, the barcode reading should be done automatically. The start of reading can be triggered via a sensor or SPS. And there are different possibilities to handle the output information. So you have a barcode reader in a similar performance range, it should be no problem at all to read the DMC barcode.
So what are the system advantages of that? If you use TactoTek and the OSIRE LED from Osram and the Melexis LED driver. The TactoTek technology brings light and sensors on places not addressable today. The OSIRE LED from Osram with the DMC data eliminates the calibration process in the supply chain. The Melexis LED driver brings the high-speed, scalable automotive robust LED driver. And together we are reducing the complexity in building, in number of components, reducing the interconnection between the modules, increasing the scalability and simplify the usage. And last but not least, we can address new applications and also a new functionality with this technology. As proof of concept, we made a demonstrator to verify if that what we theoretically worked out together, if that works. And here you see the demonstrator and the proof of concept. And if you need more information, please reach out to us. Thank you for your attention.
Thanks a lot.
All right, thank you, gentlemen, for your excellent presentation today. And now let's head over to the panel discussion, where Michael Brandl and Tomi Simula will now join us. And first up, nowadays light is seen as a more and more popular way to build a distinguished brand, whether it is used for a sleek car door trim or an intuitive smart home HMI panel. And this has made many OEMs requirements for color point calibration, stability, and hiding/showing lighting features very high. So do you see that we can create a generalized solution, or are the consumers willing to pay more for more refined functions?
That's an excellent question. I think light is emotion. So we will see more and more light inside the cars to carry this emotion. Obviously, not all cars are the same. So we will have different classes of cars with different features. Normally, the higher priced cars show more features, but it could also be brand strategy to have a more affordable car differentiate itself through a lot of light. So I believe the consumers will appreciate this emotion, and thus there will be a lot of money spent for light, just as much light as can be afforded.
How about Roland? What do you think?
If you are talking about ambient lighting in the car, you are and autonomous driving, you are talking very often about catching the driver's attention or making the roads safer. But there is, in my opinion, also another aspect, and that is the well-being inside the cabin. One is the seasickness, what you can compensate with light, and also the well-being, the temperature. I mean, with lighting, you can influence 2 or 3 degrees in adjusting the color of the light, and you feel warmer or colder. So this is for me also an aspect what we have to take into account in the future, not only driver attention. But on the end of the day, it's also how much light can we afford inside the cabin.
Yeah, absolutely. And great thing that you mentioned the self-driving car. So we can continue with that theme, as the self-driving car is going to be a space where people will spend quite a bit of time in. So if you consider self-driving mobility as a service, EVs, that they will replace some of the taxis and even some public transportation, do you see a demand for personalized experiences such as ambience or work lighting?
I mean, if you use the car on business, you have probably different expectations because you want to work while you are driving or you are driven. If you're on a private trip, you expect probably more comfortable light and also music and other surroundings. So this is definitely an aspect.
I fully agree. And within the car, I think light and sound are the ones that can be changed easiest and be adapted for me as a driver to my needs. So if I have or imagine a self-driving car which picks me up, I could imagine this car adapts to my needs. If I want to work, if I want to relax, I can probably set the settings through my cell phone. And if I have a company which allows such or provides me such a car where I can change those settings, I'm probably more likely to select this company rather than a company that just sends a car which I'm an anonymous person. So there will be for sure a differentiation possible.
Okay, Tommy, how about you? What is your viewpoint on this?
This is a very interesting point for TactoTek, because this is a deep level architecture item that we are in a unique position to address. We can, in part, address how the user can be securely identified, how the settings can be tuned, and then how they are cleared once the, for example, the car rental expires. So there's, we have a vision where only like 4 wires go inside each part, and the part is smart enough to be basically completely reconfigured over the air based on user needs. And that ideal is something that this solution from Melexis and Osram can in part help realize, in that the driver solution offers customizability that previously hasn't really been there. It's a relatively open interface, so building on that, we can easily provide the enablers, but it's only a matter of the actual end customers implementing those. So as Michael mentioned, it's probably something that's going to guide how the end users interact and how the end users make selections based on availability of these technologies. Especially in the case of self-driving cars, we of course want to make sure that there's a sense of ownership. If it may be very briefly, but that there is some, so that the experience can be, it can be you can feel that it's yours. And that's a very important point.
So ideally, there would only be power and data connections to each IMSE structure, whether it is automotive or customer electronics. And this would indeed greatly simplify the overall architecture of the part or product and reduce the need for messy wiring. IMSE vision thus aligns well with those of both Osram and Melexis, opening up some very interesting possibilities for the future. So Osram and Melexis, with your extensive experience in the industry, how do you see IMSE positioned against the needs and requirements of today and near future?
I mean, what I can say from the Melexis side is that our drivers are ready to be used in scalable systems like Tommy described, only 2 wires running in. And we can scale over our drivers for the application needed. And we have also the capability to update them over the air. So ready to go.
Yeah. Easing the application normally helps to also help the application come true. So if it's too complicated, it's not going to work. So this ease of use is a main factor for success. However, with this ease of use, I think especially the automotive industry needs predictability. Predictability means reliability, means delivery security throughout the supply chain, and much more. So combining this as friends, as Tommy said before, helps to enable only using qualified and available products and bringing into a predictable and reliable system.
All right, thank you. So thank you, gentlemen, for this panel discussion. And next up, we have the live Q&A. All right, now we have the live Q&A with Tommy, Michael, and Roland. Welcome on board, gentlemen. And
thank you.
And for the audience, please keep sending in your questions via the Q&A box on the bottom of your screen. And let's start. The first question, I think this is directed to Tommy. What kinds of components are most optimal for IMSE?
IMSE uses components in a slightly unorthodox way, so not everything will work. We've actually written a whole white paper on this. This can be found on the TactoTek website, but basically anything that's not too big and not too small, and that has reasonably sized terminals that can be expected to work. Then again, of course, there may be components that melt too easily. The polymer that we inject between typically two films, that tends to be very hot. So it can melt stuff, and that's why very easily melting materials are not optimal. But yeah, I'd advise you to check out the white paper. It's a very good, well-written paper, and that should answer most of those questions. Basically, there's a Goldilocks zone of components, not too big, not too small, just right.
Thank you, Tommy. I like the term Goldilocks zone of components. Then we have a question about the illumination thermal management, which is a topic we already touched during the previous Q&A. So is the illumination thermal management causing challenges in IMSC? And if so, how is it handled?
It does in a way. And I feel that LEDs, especially from this point of view, they have a PR problem. They are not soft, fluffy, and cute, so no one will speak for them if they are being abused. So doing designs that rely on everything having to be on full blast 100% of the time, that of course will be a problem. It will be a problem in traditional electronics, but it's even more so in IMSC. Then again, that being said, if you make a design where you don't have to rely on running the component at full blast all the time, the usual tricks work. If you have slightly too much heat, you can basically slap on a heatsink or copper or graphite tape, and that will do the trick most of the time. So due to the multidisciplinary nature of IMSC, you will need to be sure that whatever you design in, it will work with the others. So you will need to, when you're first starting to design the part, this is something that you will need to keep in mind. It's from that point of view, it's in no way different from traditional electronics. Our challenge is unique in that we have a layer of plastic between the component and the surroundings. But for most use cases, due to the unique way light is handled, as we heard earlier in IMSC, thermal management it's something that will need to be kept in mind, but it's certainly not a blocking point.
Okay, thank you, Tommy. Then we have a question for Roland about the Melexis technology. Could it be broadened into HMI, audio, sensors, and so forth? Do we have Roland on the line?
Yes, I'm on the line, but I didn't get the question, sorry.
Okay, I can repeat. So could the Melexis technology be broadened into HMI, audio, sensors, and so forth?
Yes, of course. I mean, with this TactoTek technology, we can bring light and sensors on places they are not addressable before because of the thickness of the technology. So it's easily integratable in the TactoTek technology and also scalable. So there is no issue with that.
Okay, thank you, Roland. Then we have question on the number of LEDs that are needed to create an ambient illumination for a part in IMSC compared to conventional technology. So how does the number of LEDs differ?
I guess this is more of a question for me. That, as Pasi said, or answered to a similar question earlier, the number of LEDs needed is very design dependent, and also that depends heavily on the number of LEDs needed. Michael and his company Osram, they have a very broad selection of LEDs with varying power levels. So if your application only needs a little light, then it can be done with very few LEDs. But if you need lots of light, you will either need to be able to look directly at the LED, or you will need a great number of them. We have certain aspects where there's more design freedom than in traditional cases, and there are also certain design cases where we may be practically on the same level. And there are, of course, some use cases where we may not be optimal. So there's no easy, clear-cut solution, clear-cut answer for this question. But basically, we are competitive.
Yes, thanks, Tommy. And how about Michael? Would you like to elaborate on the mentioned LEDs?
I do highly agree with Tommy. It depends on what does the customer at the end need to see. The technology, both on the IMSE side, I guess, and for sure as well on the LED, but also on the Melexis side, allows the scalability. So we can provide LEDs for a low count of LEDs inside the application, but also we have LEDs that are used in the normal world in a high amount, and that can also be used the same way in IMSE. So I don't see any limitations for the design. If you choose the right LED, as Tommy said, you can do virtually every design.
Okay, thank you, Michael. And for the audience, please send in your questions via the Q&A box, not the chat box, so we will find them easier. Thank you. Then about the color calibration. So do you have ways to accurately calibrate colors in an IMSE structure so that also the aging of the part and the components are taken into account?
Okay, this is a multidisciplinary item. In order to make a full IMSE solution, we will need at least the three parties present here. The LED manufacturer providing the initial calibration data. If it can be provided with the components, that's extremely convenient, and there will be no need to measure that later. And the stack in between the LED and the user who's seeing the light, that's something that can also be calibrated into. And I think we're going to hear more about the resin aging and resin reliability point of view from Covestro a bit later. But basically, I think that if we have basically the color of the light path measured, and Osram has provided us with the initial color point of the LED, I think, Roland, it would be trivial, near trivial, with the Melexis solution to perform a color calibration. And using the aging data available for the materials, it would also be possible to do calibration over time, or to compensate for aging, I guess.
Yeah. I mean, our driver is ready. Just in case there is an aging effect, we could have an uptime counter to count the hours, and then we can compensate this over lifetime. So our driver is ready to do that. You can implement that in software because this is a free programmable device, and we have enough memory inside to follow this request if needed.
I guess any systematic effect can be compensated. So if we have a known color shift, as Tommy mentioned, you compensate from 0 hour on. That's an easy algorithm, I would say. If there's a systematic effect over time, you can also compensate. The question is, when do you need to compensate, and what is still good enough over a long period of time inside the car to be not noticeable? Because if all the LEDs or the material around the LEDs ages the same way, nobody's gonna notice. If the aging is different between the different LEDs, this is something we have to take care about.
That, Michael, is an excellent point, because this is a design point where it's very easy to over-engineer and incur cost that no one will notice. It will bring very little benefit. But ensuring that the entire stack ages in a predictable fashion and ages gracefully, that's a very key thing for IMSE.
I mean, coming back to the aging, we measure from each LED the temperature. So if there would be an effect, we could could go down to the LED. So we don't have the temperature from the whole light guide or whatever. We can measure the individual temperature with our device. So you get very exact temperature data. So you could use them for compensation, even if it varies from LED to LED, just if needed. Yeah.
So basically the enablers for however refined solution you can think of, the enablers are there.
Yeah, exactly.
It's just a matter that at some point there's going to be difficult to find funding for the project cost for a more refined solution. There's a Goldilocks zone for that too.
I mean, to know the temperature of your application is always helpful, even if you don't use it to compensate something, just to control the lighting or the power dissipation of your application. Yeah, because that could be sometimes tricky, depending where the LED is, but we could measure that and compensate it, even if it's not linked to aging.
Yes, a very good point as well.
Okay, thank you, gentlemen. Excellent discussion. Then we have a time for maybe one question more about what is the maximum temperature LEDs can operate in?
It's easy to answer from the LED side. It's most probably higher than the surrounding environment can take. So typically LEDs can operate up to 110, 125, some even up to 150 degrees Celsius, but Tommy might not like to drive them that hard. Yes,
you are absolutely correct. The thing is that you mentioned 150. If we have 150 degree LED inside a plastic, especially for the consumer market, the plastics will start to soften, and that's not something we want to happen. So, and also since temperature drives aging, or it accelerates aging, we will want to make sure that we don't drive LEDs that hard so that they will reach those temperatures. Just as I said in response to I think that was the first question, do not abuse the LEDs, please.
I mean, from the IC side, we can go up to 117 degrees. So we could probably burn a hole into the plastics. I'm not quite sure.
Yeah, you would see some rather interesting effects.
All right, thank you, gentlemen, for this interesting question. It's now time for us to move on with the program. So thank you again.